Minecraft Java Edition Redstone at first glance functions exactly like you'd expect. Torches invert signals, repeaters extend them, and observers create pulses when updated. You power a component, it has a certain delay, and then it does its thing. But that isn't always true. And today we're going to answer what happens in circuits such as these. First, let's answer how we can use these mechanics for redstone development. Well, what if I told you that these seemingly unpredictable mechanics can be used to transmit a theoretically infinite amount of data in one signal, make events happen seemingly instantly, send any amount of data to any point in the world, bypassing unloaded chunks, and a lot more beyond that. Everything in Minecraft is processed one after another every tick, which there are 20 of in a second, so each is 50 milliseconds. The game is single-threaded, so if two components change state in the same tick, one of them has to go first, and as it happens we can both control and check which one that is. By far the best feature of the system is how deterministic it is. Imagine a bunch of drawers in a line, a separate one for each tick. Each of these drawers will hold redstone events that are scheduled to happen in it. For example, assume we're in the first drawer, and an observer is scheduled to turn on, which powers the repeater with 2 ticks of delay. The repeater is placed in the drawer, spaced apart by 2 game ticks, so it's 2 drawers down the line. I will from here on out in the graphic only use even game ticks, as most components have even game ticks worth of delay. So what happens when 2 components are in a drawer? Well, if they have the same priority, yes, I'll address that later, the first one to be placed in will be the first one to process its output. So, for example, if 2 repeaters are set to activate in a tick, let's say one is powering a redstone torch and the other a comparator, the first repeater in the drawer will activate its component first and schedule it 2 drawers ahead, after which the other one will. This also implies that those components will maintain the ordering of the repeaters and can pass it on again. But, as I mentioned, we can control these priorities, right? So what's the catch? With this understanding, all we can do is transfer priorities that already exist. Or can we? As we mentioned earlier, a component with more delay will be put further in the drawers, and assuming that if a component is put in a drawer earlier, it will be executed earlier, we can sort of control the order things go in. For example, a 4-tick repeater will always go before 2 2-tick repeaters, and a dispenser will always go before 2 observers or comparators. Well, not always. Unfortunately, it's not quite that simple, because you see, each drawer has multiple priorities, or compartments. There are 4 different priorities. A neutral one, assigned to all components other than comparators and repeaters. A high priority, assigned to repeaters turning on, and comparators with a comparator or repeater in front of them. A very high, assigned to repeaters turning off. And an extremely high priority, only reserved for repeaters with a comparator or repeater in front of them. So, let's start with a very simple example. Why doesn't an observer trigger a torch or comparator? Well, this is because torches and comparators check for input in the same tick as they turn on. They also have an equivalent neutral priority to the observer. So here's what happens. Observer turns on and schedules itself to turn off. It then schedules the comparator and torch to change state. Do you see the problem? The observer will turn off before the components are supposed to change state, so the component's state won't be affected by the scheduling because they will check for input after that happens. But something really mind-boggling happens when there are 2 observers, because one of them turns on first and schedules the comparator or torch, and the second one turns on after that. That means that the second observer will still be on when they check for input. So 2 observers do work with this. Additionally, a comparator with a repeater or comparator in front of it will also respond to a singular observer because, as we mentioned earlier, this increases its priority, hence it will check for input before the observer turns off. It's also important to note that a repeater turning on will respond to any pulse length because they always turn on when scheduled. We can apply the same principle to show that if we were to turn a pulse on in the same tick as the comparator checks for input with a higher priority, it would read that signal in the same tick as it receives it, basically instantly. This is a very basic form of comparator priming, a way to do instant comparator logic. Let's take a look at another example. In a repeater chain like this, the last repeater has some funky priorities. If we input a 5 Hz clock, meaning it flashes 5 times a second or every 4 game ticks, into a repeater chain, the last repeater stays on. This happens because all repeaters but the last one have a repeater or comparator directly in front of them, so they get a buff to their priority. This is caused by the repeater before it, because the repeater always turns on before the one in front of it is scheduled, and it can only schedule that repeater in its own respective priority. The repeater, however, never has a big enough gap to turn off. So I have hopped in game, and we can take a look at a way to fix this problem. Effectively, what happens is that because this component before the last one has a higher priority than the last component, it creates a bottleneck. So this repeater will turn on before this one has a chance to turn off. So this one checks and sees, hey, I'm still powered. I probably shouldn't turn off. But as we know, a comparator that goes directly into another Tiletick has the same priority as a repeater going into air. So a possible solution is this one right here, which basically ensures that all of the components have the same priority. So if we check, this works flawlessly. Another solution would be to break up the line to make sure there's never more than one in a row, which eliminates the need altogether since they all have the same priority and none of them get boosted. This also works. Now I need to make a simple distinction between global and local update order, meaning the order components activate in. Everything I've explained so far is global, whereas for example, using the order rails or walls update in is fully local. This means that yes, rails and walls will schedule things in an expected order, but that order will not be global. It will instead all basically have the same priority as the thing triggering the component. For shape updates, so the kind of updates observers measure, for rails it extends from furthest to closest from the source, and from walls downwards from where it is powered. Now this is all fine and dandy if we want to order a bunch of things in a line somewhere. Like this, for example, will order the piston from furthest to closest from where it is powered. And of course, we can change the order. This is very useful. However, what if we have a third piston and we don't want it to go in the order from left to right here, for example? We want it to go this, and then this, and then this. Well, that's a bit tricky. Of course, you can take 3 observer outputs and you can wire the center observer to the last piston and this observer to the middle piston. However, that's not very convenient, and it also still requires the rail update order to go in the right order. What if you could simply use global update order to encode a line that directly gives it a certain position in the update order, no matter how it's powered, no matter from what it's powered? Well, that's what this does. These are called priority lines. Effectively, what you can do is you can encode a certain order in them in binary. Here we have 3 command blocks, one that says left, one that says center, and one that says right. If I power them right now, they will go from the right to the left because that is the order that the dust powers them in. But what we can do is we can give them a certain number. So let's say we want this middle one to go first. We can just have number 0 on it. That is not a problem. Then we want the left one to go. We'll give it a 1. And then the right one, we'll give it a 2. So this will go center, left, right. We can also do numbers higher than this. So we can say, hey, we want the left one to be 5 and the right one to be 7. So it'll go center, left, right again, but there is space in there so we can put other events to happen. And indeed, this is not local. If these components are powered in the same tick, no matter where in the world they are, no matter what powers them, they will always go in this order. So here we have a little demonstration of that. Of course, they do have to go in the same tick, which is why I have to add 2 game ticks of delay here and 2 game ticks here for the dust to reach. Let's say we want this middle one to go last. So we go that one, that one, that one, that one, and then that one. So we want this one to go first. It can be 0. Then we want this furthest one to go after. 1, 2, 3, and then this one will go last, so it will be 4. So we will see far left, far right, right, left, center. You can even change these priorities programmably with a circuit such as this. In the wireless community, this is called a channel selector because it lets you select when exactly in the tick you're doing something. The circuit is very simple, basically just two components, a repeater and an observer. Because they get in the same signal, and the repeater has a high priority, it will always override the observer's pulse. Unless, of course, the repeater is locked, in which case you're basically changing this repeater to a comparator, or in this case, an observer. So we can input, let's say, 3 here and 1 here, and we know that the 3 here will happen later. So this will go right and left. And that, of course, happens. We can also say we put a 5 on the right. So this will go left, right. And this works for any amount of nodes, given that they power in the same tick. But of course, of what use is an order of signals to us if we can't check what the order is? Of course, we used command blocks back there, and you might have noticed I've also used pistons, which yes, you can do. But this is not very clean, especially if you want to do solid state logic or if you want to have a lot of these comparisons. Another simple solution would be to use a comparator and a repeater in a situation like this. So basically what is happening here is that because the comparator has another Tiletick in front of it and has the same priority as a repeater without any in front of it. So this is the same as using two comparators like that to have the same priority so it doesn't bottleneck. But in this case, because this comparator and this repeater turn on in the same tick, if the comparator turns on first, it will actually lock the repeater in an off state. So if I do that, notice it locks it before it turns on. But if the repeater is scheduled first, it lets the signal through. And it does also extend it, so it creates a 4-game tick signal. Another alternative is a circuit such as this. In this circuit, what happens is that effectively, the same thing happens, but with a comparator blocking a torch from turning on. So basically what matters here is if this comparator turns on before this torch tries turning on. So if I power it here, this comparator will turn on before this torch checks for input. So it'll already be on. And if I power it on this end, that will happen after. Of course, you may also be wondering, is this useful on a global scale like you said, because you do actually need the signals to be synchronized? How do you do that? That sounds complicated. Well, it's not as bad as it sounds, thanks to one neat little component, the daylight sensor. Daylight sensors will always, no matter what, update tied to a 1-second grid. So if I update this daylight sensor, it will generate a signal, and if you check, it always syncs up to exactly 1 second relative to the same timing, no matter where it is, and this is true for all daylight sensors. So if I update this one, you'll see that the signals will sync up. Of course, this only works because I have a 1 second loop here. Now, this itself is not as useful as is a pure daylight sensor clock that uses the daylight sensor for every cycle, because this can still be unsynced via reloading or some other problem. But it does have one neat feature, which is that they will keep the same order that they were powered in. And this is true for any signal which is looped. So, if you see you have a circuit like this, which uses a comparator going out of a daylight sensor blocked by an daylight sensor that doesn't have a block above it, this will subtract the idle daylight from the modified daylight, meaning that this clock works at any time of day. And it produces a signal once a second. Of course, things are never as simple as they seem. Each one of these 4 base components, as simple as they might seem, have a lot of extra depth to them, a lot of extra complexity that I cannot explain in this video, or it would be 30 hours long. Not really, I'm of course exaggerating, but it could be a standalone video. For example, the repeater will always turn on no matter what signal length it has input of, because no matter when it's scheduled, it will always turn on
But the torch and the comparator, for example, don't have this feature. They need to have a signal in the tick that they turn on, or else they won't. The observer as well will schedule itself to turn off no matter what, but it can also be scheduled by other components to turn off if it turns off before the observer itself does. It's kind of weird. This is called the observer bug. So here, for example, is another quirk. Observers will, of course, schedule themselves to turn off. But in a circuit like this, it has a really weird behavior. Basically, an observer will send a block shape update before it schedules itself to turn off, then it will schedule itself to turn off, then it will power whatever it's powering. So in this case, what'll happen is it'll go, this observer will turn on, then this one will turn off, then this one will turn on. It's very weird. Of course, that's not even to mention intended behaviors of components. For example, repeaters being able to change timings, comparators being able to be scheduled when they already have signal strength in them, torch burnout, or the very odd timings of observers. Of course, none of this is to discourage you. This is simply to show that Minecraft is absurdly complex and that there's always something to be looking forward to learning. The game is so complex, in fact, that there is not a single person that comes even close to understanding the whole thing, and I think that's impossible.
Now let's take a look at the technologies I promised at the start. I'll briefly introduce them here, as most of these will eventually have their own dedicated video. So, I promised infinite data transmission, right? What gives? Well, theoretically. You see, because each signal can have some priority relative to any amount of other signals, it can hold an infinite amount of data in its position. So how would that look in practical application?
Here is such a circuit in practice. We get a signal from our clock and encode it into 5 different priorities. 3 for the data and 2 for the reference. Basically, the data will be either before, in between, or after the 2 reference signals. And the 2 reference signals will be sent alongside, which at the end we will decode their priority. Effectively how this works is that we have these 3 redstone torches. This one is in between the 2 reference signals, this one is after, and this one is before. There's a very good reason that the middle one is before. This has to do with the fact that when 2 bits are triggered on the same signal, all 3 of them will trigger. But because this one is the earliest, it will override the other 2. Otherwise, only the left or the right signal will trigger, using the priority of its respective signal. Then, at the end, we will decode this using these comparator repeater checkers, as we've mentioned before, which are very neat, especially for this kind of vertical setup. And doing a bit of logic, that is decoded to get your bits back in the correct encoding.
But what about actually doing instant logic as I mentioned in the intro? Well, we did go over how you can actually schedule a comparator without powering it. So what if you provided a signal, as mentioned, comparator priming? In this case, the observer will schedule the comparator and then it will not turn it on. But in the same tick as the comparator is supposed to turn on, this repeater will. So this repeater will turn on in the same tick as this comparator will turn on after it, which means that this comparator will forward the same signal as the repeater outputs. So we'll have the repeater signal here and the comparator here, 14 here, 14 here. And that does work. And of course, you can do this in a line. So in a setup like this, if you were to boop, you can see that that does work. But there is a little caveat to how I did it over here. Because I primed the comparators from the side, they need to always have a signal. So if I were to subtract that, you'll notice it takes a little extra time to get there. But if I primed it from the back, obviously I could subtract that signal. For example, if I do it here, and I grab a lever, that works fine. You can also do this in 2 game tick intervals, or 10 Hz, because there's 20 of them, so 10 times a second, with a setup like this. It uses this observer here to schedule the comparator, after which this observer will schedule this observer, meaning that this observer will turn off, then the comparator will be scheduled, then this observer will turn on afterwards and schedule it as soon as it's done being scheduled. This then loops around, And you have this from that direction to this one here. As we mentioned, rails are from furthest to closest, and it works. And you can do that. And if I check here, that is instant, and it goes through all of them. Pretty foolproof. And yeah, you can do a lot with this. In fact, as I said, you can do any logic with this. Here is a 10 Hz addition circuit. It takes in two numbers, in this case 16-bit, and it outputs a result instantly, and you can do this 10 times a second. Now let's talk about wireless data transfer, a concept first thought up by Cycraft member 202name, very smart guy. Basically what it boils down to is that every item has a number attached to it, its entity ID. This also accounts for armor stands, minecarts, and really every entity, but it's most useful with items, because with items we can measure the difference between two of them. Effectively how this works is that this number is used to separate items into 4 groups. So it'll be 2, 3, or 1, 2, and then, it'll repeat, and after the 4th group it loops back around. So it's 4 and then 1. And these groups will determine how many game ticks an item waits after falling. So you see, one of those fell first, the axe, so it's probably in an earlier group than the one that fell later. Then this is very useful for us because if we drop an item and another item, we can measure if these are exactly one group apart. And if they are, an item didn't get dropped in between. And if they're 2 groups apart, an item got dropped in between. Effectively, how this looks is like this diagram over here. There's 4 starting positions. And if the item is in group 1 and the next one is measured without any difference, it's in group 2, 2 and 3, 3 and 4, or 4 and 1. But if an item is dropped in between, this is the pattern that we get. This is the difference here that's created. Effectively, how this can help us is because we can measure this state as an output of, for example, over here, these comparators, and we can detect if it's this, we receive a 1, and if it's this, we receive a 0. And this is very neat for us because if we check, it's actually very simplifiable. In this case, they're always 2 game ticks apart. So for example, if we say take a 2 game tick output out of every one of these signals, we get a 4 game tick output in all of the cases here, but here we don't. And a circuit such as this filters that out. So to reiterate, we use a 24/7 compatible daylight sensor clock to generate a pulse. We use priority lines to get the correct orderings of the items, and we take the output of the items after being laid on the trapdoors to measure them, and then we compare them in this circuit here. What this circuit does is it converts them to a 2 game tick pulse. Then it checks if it's 2 separate pulses or if it's 1 4 game tick pulse. So this fixes the edge case, which is this one right here, which gives you 2 game tick pulses with 1 game tick off in between. And this torch will ignore that. Then it checks if the torch is off for 4 game ticks or for 3, because it can also be 3 in those cases. And that isn't via this lamp. It takes 4 game ticks to turn off. And the observer here will give us an output. This is very neat. Additionally, the trapdoors are also controlled with the same signal, which it opens for 4 game ticks, which is also the delay of the dropper. It's very neat. So if we test this, nothing happens, obviously, because I haven't started dropping the item here. But if I do drop the item, it does get in between, and this starts activating. Just for good measure and to show the utility of the wireless tech, plus I like to flex, here's a network card designed using these systems. Using the beforehand mentioned channel selectors, we can basically skip the whole routing, and we can just go directly to that address. Additionally, there's a lot of stuff in here that I really can't explain. It's super complicated, and of course this will be getting its own video, probably gonna have to be hour long. But yeah, you can do a lot with this stuff. And of course, you can do a lot more than just networking. You can do radio, networking, even survival applications, right? You can control mob switches, you can do stasis networks. anything your heart desires, and it works all over the world, and it has infinite range, right? So, go crazy. But there is one more thing I want to show you guys before wrapping up this video, and for that, I will have to hop into Spectator. So what this is, it's a sorter of binary values using Tiletick priorities. Here's how it works. So you take each of these binary signals, and you convert them to a signal through a channel selector. So you go down here, and you'll see we lock or don't lock these repeaters as we do in that channel selector design. Then at the bottom, we obviously get out our signal, which is this right here. This signal is sort of split into two, as you'll notice. It goes up here and it goes down here. This one that goes up here will be later than the repeater being scheduled. So what'll happen basically is that each one of these signals will first schedule their repeater and then the signal above. But this order does not override the Tiletick priorities. So effectively what happens, right, is that we get one of them that will have this repeater activate before all other signals reach this. So then we compare the priorities and we get out the earliest signal. Then, we cancel that to inverted because this priority comparison circuit is inverted. And we loop it around and we get our output. And then that output is used to pass through the value. So if I hop into creative, we get our values in order. I didn't really bother inputting values. Let's do like 3, 5, whatever this is. I think it's like 12 and 7. And obviously, it's going to sort all of the ones first because I didn't encode all of them. So it's going to be 1 for a bit and then 1, 1, 1, 1, 3, 5, 7, 12. But I am afraid I have to wrap up this video. If you enjoyed the content, leave a like, subscribe, do the whole thing, the bell thing and the stuff. I will be leaving a world download to this little section in the description. And, a couple other sources to check out, a couple other YouTube videos. If you don't know binary, I'll leave a link for that as well. And, have a good time, have a good day, have a good evening, whatever your time is. And yeah, I'll be back next video. Bye.